Okay, I think we can start. So it's my pleasure to introduce today's speaker, Chaim Goodman-Strauss, who is an old friend. Actually, first time we met was 30 years ago. This was Summer Geometry Institute at Smith College. I think Chaim was a graduate student at the time. I was also 30 years younger. And it was a great 1 month, probably the best conference I ever attended, summer school. Chaim was visible there. He walked around with a sack of mathematical models, paper, carton models of polyhedrons, such things. And then we became colleagues at the University of Arkansas, where Chaim worked for a long time, but not anymore. So please disregard this University of Arkansas affiliation on the ad. We had a geometry seminar, I remember, mostly two speakers. I was talking about things I found interesting, and Chaim was talking about things he found interesting. And since then, I know this term, Einstein, one stone or one tile which tiles only aperiodically. And that's the topic of today's talk. You all know that there was a huge splash, breakthrough. Now this problem is solved, and that's what Chaim will talk about. If you have questions, please ask them in chat, and I will interrupt the speaker and read the questions. He doesn't mind at all. And without further ado, Chaim, please.
Well, thank you so much for the introduction, and thank you for having me. And it's a delight to be here, and it's a delight to talk about this subject, honestly, because I have been thinking about it all this time. And so, so let me just begin. So I'm at the National Museum of Mathematics in New York City. I mainly work with kids, though I also have time to do this kind of thing, and it's great. So if we want as much high quality mathematics in the world, we have to start with the little kids and draw them in and find them, look in places that we might not be able to, kids that may not have access to mathematical ideas, which is essentially most kids, unless we make the effort. So it's a great privilege to work in a setting where I can help try that. Obviously, this work is joint with none other than Dave Smith, who we'll talk about, and my colleagues Craig Kaplan and Joseph Myers. So I think it's not, I'm going to just sort of, rather than having a big buildup to the punchline, I think I'll just begin. I think we know, many of you, about the so-called Hat, the first known aperiodic monotile, which of course I'll define those terms shortly. And, I had the word sensational on this slide, the sensational discovery. That seemed a little bit immodest, but I'm not, it was not my discovery. Let me emphasize that. I'm on the team, but it was Dave Smith's discovery. So in that sense, I can perfectly modestly say that the discovery is sensational, because it really is quite amazing. And then on top of that, we had immediately an infinite continuum of aperiodic monotiles. They're essentially the same. They're combinatorially equivalent, which is a definition that doesn't quite exist. So there's a whole new need for kind of a understanding of what these kind of combinatorial tiling systems are. So that's a nice new direction for us. But then on top of that, as if it just couldn't help but, it was like, it was absolutely unreasonable how much this example gave us. It gave the same family. There's a so-called chiral aperiodic monotile, which doesn't use reflections. So there was some concern among some parties that the other two tiles, you would have both left and right-handed versions. Well, just to silence those people, here's a so-called chiral one that only requires tiles oriented the same way. Okay, that's fine. Now, the thing is, the deeper question, which really kind of goes across, really, I think, all of the sciences and mathematics in some sense. I use the word shape. When shapes fit together, how complicated this can be, but I really mean little gadgets of any kind whatsoever. So if we have little tiny atomic gadgets, which could be molecules, they could be logical fragments, they could be physical shapes. When they fit together, how complicated can this be? And of course, all around us, we have this incredible complexity. And so just to look at the real world for a moment, once we start fitting things together, we have phenomenal complexity. So just simply the way proteins or even simpler molecules like these lipids fit together is pretty fascinating and interesting. I was at a conference. Well, the hat tiling, of course, has gotten me invited various places I wouldn't normally get to go. And so one of the places I went to was a conference on people looking at soft. Well, this is a dinoflagellate. This is self-assembled from little pieces. You can see sort of the same pieces, replicated to form this thing. Kind of spontaneously comes together. But what I was going to say is that, so in soft matter physics, people are very interested in how things might fit together. And in the year 2023, so we're a quarter of the way through the 21st century, this is about the state of the art. I'm not kidding you. The state of the art for soft matter condensed physics seems to be, like, in terms of how things might fit together, is just simply really like things like, how can spheres sit inside of a cylinder? How complex, just understanding that in any kind of analytical or qualitative way. And so I took this photograph. This is actually beyond the state of the art for soft matter physics. It's like how lemons might fit into a bucket. And that's kind of funny. As a mathematician, we should wonder, well, what's a mathematical question that could even be approached here? It's not obvious that, like, could you fill up 99.7% of the container or something like that? It's a mathematical question in sort of a lowercase m sense, but I don't think it's necessarily appealing as a mathematical question in the sense of an uppercase m, a humanly practiced endeavor. But it's still worth realizing that at this exact moment, that this is beyond the capability of essentially anybody to really fully appreciate or understand how these things work. We're still at the point, for example, where we don't know what the maximum packing of tetrahedra is, for example. So very, very primitive. But we can answer questions like this. I'm sure that all of you are very good at this kind of thing. So, like, can copies of this particular shape form a tiling? So what I mean by that specifically is, can we take congruent copies of this and cover the entire infinite plane without gaps or overlaps? And I think the answer is just so obvious, it barely merits discussion. But at least it does give us a chance to define what we mean by tiling. That's to say, again, and tile for that matter, we're using compact, closed topological disks with piecewise smooth boundaries, if you like, whatever. And we want to fit them together without overlapping interiors. And I think this is not a big surprise there. Okay. But then this one. So this one, of course, you can pretty readily determine the answer. Does this admit a tiling? And so to introduce the word monotile. So a monotile is a shape, that is to say, again, a closed topological disk with piecewise smooth boundaries, if you want. But anyway, is this shape a monotile? Meaning, can I use it to actually cover the entire plane in a tiling, to form a tiling? And of course, I think you all realize, no, it's not. And you can come up with a quick argument probably by just trying to stick I think you can see my mouse. Is that right? You can see my mouse. So you can, for example, make an argument by trying to stick a point of the star there, and immediately you see there's no room for a second star, and that's pretty obvious. But the real question here is, okay, would there be an algorithm to determine this? Is there some sort of process that we could check? Okay, well, in some cases we can do pretty well. So Casey Mann was a student of mine at Arkansas, and Sergey knows him or knew him. And Casey became an expert on this question. And he came up with lots and lots of examples. And this one we can pretty well prove very simply cannot tile the plane. And this is a fairly common strategy. Whoop. Uh-oh. Okay. We can see that we can see that it can tile this much, that it can tile what we would say 3 concentric rings, 3 so-called coronas. We can fit this many, and this many around. And you can see that there's some sort of problem with a whole lot of sort of these circular holes. And that seems to be pretty much what's happening. Maybe there's another way to escape that. But we can see no, that's impossible. So if we look more closely, this is actually it's really 4 hexagons. with where the edges of some of the hexagons have been replaced with either indentions buckling in or extensions, bumps sticking out. And you can count, there's, I believe, 7 in and 3 out. So in any actual interior of a tiling, in any actual interior of a tiling, we would have to have every innie meeting an outie. And so we, of course, have to have the same number of each. There's this imbalance. There's more innies than outies. And so that balance has to occur completely on the boundary of this patch. Well, the number of tiles is roughly growing by the radius of the area of this patch. And the perimeter, where we can have some problem, is growing like the circumference of this patch. And over larger and larger radii, asymptotically, the number of tiles is growing quadratically while the boundary is only growing linearly. And sooner or later, the quadratic beats the linear. And that's what happened here. So we got to 3 rings, and then the linear part describing the length of the boundary was just not sufficient enough to contain all the error. So that's a fine argument. So we use the Haish number, or Haish, I just learned. If somebody is Dutch, I apologize, but I believe it's Haish. The Haish number is a measurement of how badly the tile behave. A non-monotile isn't a non-monotile. That's to say, how far can we go out before things go bad? And so this is a famous example. This is a Robert Aumann, who was another so-called amateur mathematician. He worked in the post office for most of his career, but he contributed a great many of the important examples in this area. So this one has, if we count, 3 rings, and it might have a 4th ring if we count these holes in it. They don't quite meet, but we just by convention call this 3. So this would have a Haish number 3. This is the current world record, which is Haish number 6, due to Boschik from just 2 years ago. And I believe this was published in the Intelligencer, Sergey, was it not? And that's so.
Yes, correct.
And so, so then the question naturally is, are these so-called Haish numbers unbounded? Is there, for any n, is there some tile that has a Haish number of greater than n? But we know now that this is the current world record. Okay, well, that's fine. So going back to 2003, one of my co-authors on the Hat paper, Joseph Myers, was exploring sort of the opposite question, which is he was looking at tiles that could actually form tiles. This is a monotile, but another measure to say how complex a monotile might be is if it tiles periodically, what's the smallest possible fundamental domain that this tile can have? And so by exhaustive computer search, Joseph was able to show that this is actually the smallest possible fundamental domain by those tiles. This tile does tile periodically, but it can't do any better than this. So the isohedral number is a measurement of how complex this is. And in particular, it's the size of the fundamental domain and counted by tiles. And this has isohedral number 10. This is the current world record in that direction. But just to show you how bizarre this is, oh, well, of course, the question is the isohedral number unbounded? And we don't know that either. Just to show you another example, this is from the same era, from the same computer search. This is the second best example with isohedral number 9, where 9 separate tiles, or at least 9 tiles, are needed to form a fundamental domain. And of course, I've colored the tiles, I should say, by their transitivity classes. That is to say, their orbits. That is to say, the ones that are colored the same are in the same positions relative to the whole as any of the others. And of course, also, I chose this fundamental domain. I could have tweaked that in various kinds of ways. That doesn't change the point whatsoever. So this is more or less the state of things until pretty recently. We had these examples, and we can tell that, okay, things are confusing. Like how confusing is this example? Well, this was found by a computer search, and I was very curious, is it even at a human scale to even determine whether or not this tiles the plane? Is this actually a mathematical question in the sense that a human being can actually solve it and appreciate the answer? Or is this just something that requires well, it certainly requires brute force. And all I know is that I, at one time, had an extra $100 that I'd gotten for free from somebody else. And I offered it I announced from the stage at a convention where there were a lot of puzzle solvers, that the first person who could tell me whether or not this thing tiled periodically would get the $100. So I know that a highly motivated, highly capable human puzzle solver can do this in half an hour. That's what I bought for my $100. So I know that it is human scale, but just kind of barely. So, okay, so again, we want to know is isohedral number bounded. So now, what would be an algorithm that could determine whether or not a shape could be used to form a tiling, to determine whether a given tile admits a tiling? And so the basic strategy is sort of obvious. You would just enumerate larger and larger patches specifically covering larger and larger disks, round disks. And so we can eventually find out that if that a tile does not admit a tiling, because if it doesn't admit a tiling, eventually we'll get stuck. We'll just run out of some size disk that we can no longer cover. And so that's a finite algorithm that will halt if the tile does not have a tiling. But I should add that if the tile does admit a tiling, this algorithm will not halt. And so in particular, then if there were a bound on Hayes number, we would have a decision algorithm for the so-called monotiling problem, which is just enumerate patches, and then you keep enumerating them, and either you reach that universal bound on the Hayes number, and then you're home free. You know that you're going to be able to finish, or you'll just run out of possibilities, and you know you haven't tiled. And in the same kind of way, we could do this sort of the same kind of algorithm to discover whether or not a shape admits a periodic tiling. We just simply enumerate larger and larger patches, and as we go, we just sort of check. There's various simple-minded ways to check to see that we have a fundamental domain or not. And if it is, okay, so we have an algorithm. So just to introduce the definition, the key definition of the entire subject is the word aperiodic, and the word it's a monotile is aperiodic if it cannot form periodic tilings. I think this is a pretty sophisticated group. We know our quantifiers. In the real world, out with the press, this was, of course, an endless problem. It's not aperiodic if it can form non-tilings that are not periodic. It's a monotile is aperiodic if it can only form tilings that are not periodic. In other words, so it has to form tilings to be called a monotile, and it can never form periodic tilings. And if there were such a thing, which I think we know the punchline here, but if there were no such a thing, then we'd have a method to decide the so-called monotiling problem, the question of whether or not a shape admits a tiling or is a monotile. And so we have this first decidability little box here, little implication box, which is in general, and this is more general as I'll discuss, I think. If the so-called monotiling problem is undecidable, which remains open, then that would imply that the Hayes number is unbounded, and it would also imply there exists an aperiodic monotile. We actually now know there exists an aperiodic monotile, as I'll get to, but the remaining two questions are still open. And I think probably the most interesting and difficult and kind of compelling question remaining here is this one. Is it actually decidable whether or not a given tile admits a tiling of the plane? And I'll put that in some context in just a second. And then similarly, the flip side of this is we could have something called the period problem, which is, does a monotile admit a tiling that has a period, has a finite fundamental domain, if you will? And if that were, we have the same kinds of implications. I guess it might be easier on the right to say the contrapositive. If there is no aperiodic monotile, then we have a method to decide the period problem. And similarly, if there were no aperiodic monotile, we'd have a method to decide the monotiling problem. By the way, I guess I should say, I always forget until well into the talk, but when I say undecidable, I specifically mean computationally undecidable, not undecidable in whatever the other, in the completeness sense. So, and then we have the same implications. So this is sort of the big bang of this entire subject is that Hao Wang, who is wrapping up one of the cases of Hilbert's so-called Einstein problem, which was, there's a given first order formula have a model that satisfies it, whatever. Anyway, the point is that he was encoding symbolic fragments. Symbolic fragments have to fit together in certain ways that they match. They really match. And so he was encoding various kinds of things as tiles, and he came up with this thing. This is just clipped out of his paper. This is over 60 years old, so of course the language is different. But a finite set of plates is solvable. What he's asking there is a finite set of tiles admits a tiling, and he's conjecturing that if and only if it admits a cyclic rectangle, that is to say, if and only if a set of tiles admits a periodic tiling. So he's claiming here that he's basically saying that he believed that there would be any set of tiles that admits a tiling would admit a periodic tiling. And then in 4.1.3, he's making the point I just made, which is that if that were so, then we would have a decision algorithm to determine whether or not a given set of tiles admits a tiling of the plane. And so today, the slightly more general version of this, here we allow more than one kind of tile, is that if the so-called domino problem is undecidable, then there must be an aperiodic set of tiles. And he conjectured this, but he actually knew that there was an undecidable tiling problem. The completion problem is very easily shown to be undecidable. So let me talk a bit about that. So of course, Turing machines are the touchstone, the wellspring, if you will, of what we might mean by of computation in the first place. And it's amusing to think about running Mac OS or something in Turing machines, but in principle, it's possible. And just to sort of clarify what I'm saying here, so we have an infinite tape with, say, zeros and ones on it or whatever, some alphabet. And at every moment, we have a read-write head that's at some position on the tape. It's in some state, A, B, C in this case, and we might be reading a letter 0, 1. So if I'm in state A, reading a 0, the instructions tell me to write a 0 on the tape, leave a 0 on the tape, move 1 to the right, and go into state B. So this transition here is is captured by this command here. And so over time, we just proceed. And then we have one special state here denoted H, which has nothing. If you get into state H, you're stuck. There's nothing, there's no instructions. So you just stop, and that's the end of the calculation. And so famously, of course, there's no decision procedure to determine whether or not you could take in this input and determine whether or not you reach the H. Of course, you can just run the machine, and that'll tell you if you do reach the H, but if you don't reach the H, you just will never quite know the answer. So this is very, very amenable to encoding as tiles, because you can look at this picture on the right and just, even though this is an infinite picture, those tapes go on forever and ever, the run might go on for arbitrarily far, but if you were able to inspect everywhere but with finite vision, so look everywhere but only with finite vision anywhere, you would be able to detect whether or not there's a problem with that picture. You can detect, is this really faithfully recording what a B should be reading and doing? So B reads a 0, it did write a 1 on the tape, it moved to the left and went into state A. See, that the picture tells me that, and I can tell if this picture did not show that, I would show that I had violated this rule. In this manner, we can convert the picture into a collection of tiles with decorations that are just the decoration showing what the machine was supposed to do. And so here are the tiles, and this set of tiles will be able to tile the plane if and only if we never reach this special tile, which has nothing that matches with it. Well, actually, I lied a little bit. This set of tiles certainly can tile the plane. It can tile the plane with just the blank tile. So that's no good. The actual statement is that the completion problem is undecidable, meaning that if I start with a particular seed configuration, namely this one, once I place that seed down, then everything else is determined, and then the run of the machine has to be encoded. This seed tile ensures that the tape is set up to either side and that the machine starts running, and then we can determine. So Wang thought that the completion problem was he knew that the completion problem was undecidable, that it could would be no procedure to determine whether this we reach the halt state, because then we would have a procedure to determine the halting problem for Turing machines. But nonetheless, he conjectured that the domino problem, if we don't necessarily require any particular tile to be placed, like how do you get rid of that blank tile, was basically the condition. And so anyway, within a few years, his student Robert Berger gave the first collection of 20,000 plus tiles, and we'll talk a little bit about that. He used this specifically to show the undecidability, but his hierarchical method became the basis of many other constructions. And so here's how it works. And so this is, I suppose, what I spent a bunch of my career on. So this L tile, for example, is not an aperiodic monotile. You can fairly readily think of ways to tile this with the L tile that's periodic. But you can form non-periodic tilings by this kind of rule. You take the tile, you inflate it into a larger copy and subdivide. And in some manner, which seems intuitive, you can if you can do this arbitrarily often, you can cover larger and larger disks, and in some sense, you can demonstrate tilings of the entire infinite plane. Now, what I just said should sound obvious, but in fact, upon reflection, it's not the least bit obvious. There's actually quite a bit of work to, show that this does what it does. But basically, it's fairly standard arguments. I guess it's often called bicompactness, but that doesn't really, to me, sum it up. If you know anything about Koenig's lemma, that probably is the simplest way to say what it really is going on. So, but basically, believably, if you can make larger and larger patches, you can cover the entire plane. And so in this way, we can form these so-called hierarchical tilings. And what does it mean? It means that we can recover the hierarchy from the tiling. If I look back at this thing, it looks certainly periodic and like something's going on. But if I mark you can actually uniquely recover that any given tile is in a L tile of the next size, is in the next size up, is in the next size up, and so on. And that's just uniquely visible from the tiles themselves. You didn't need the markings. You can recover this just by looking at it. It takes a little work, but you can see them. And so this implies that it's non-periodic, because given any translation, suppose that I had like this was allegedly a translation that left the tiling invariant. It could not have, because there's some super tile bigger than that that's going to land on top of itself. And you can actually see some problems. But another way to see the problem is look at that tile there. That tile there was in the hierarchy from the original L's. It was also in a different hierarchy from the shifted L. But the whole thing is that every L tile, every individual tile is in a unique hierarchy. Therefore, this could not have occurred in the first place. So these are non-periodic. They're necessarily non-periodic, but the L itself is not non-periodic. So the game here in general has been to construct sets of tiles that somehow enforce these hierarchies. And since I have this ready, I just want to show you. I actually have with me, I have wooden tiles of basically all of this stuff. I don't know if you can see my particular view, but here is the, and maybe if I pin myself, I don't know if that helped or not. In any case, here's these little guys. And the point is that somehow by some magic or another, the only possible thing that they can do is to form larger copies of the same kind of structure. So here I began with 4 tiles arranged like around a larger L, and now these sort of form a larger L still, although it's turned 135 degrees. So in any case, this is an example that I found shortly after moving to Arkansas 30 years ago. So since I can, let me take a moment to explain Berger's proof, because just a quick hint of it. So the idea was basically that, I showed you how Wang had described how we can emulate Turing machines. Berger's idea was just simply to use these hierarchical tilings to sort of find structures within them that repeat over and over again, and then use those as the kind of sandbox. So we have this kind of a sandbox for running Turing machine simulations. We do this kind of in this attenuated way, which I won't describe right now. But basically, the dark shaded squares are the only correspond to the original cells of the Turing machine. And the rest of this stuff is just sort of stretched out and spread out and sort of flowing around other smaller sandboxes here. And then further larger sandboxes are flowing around this one and ad infinitum. In this way, it gives us a way to emulate the run of Turing machines over arbitrarily large things. All right. Well, anyway, roughly equivalently, there's all kinds of NP-complete problems. NP-completeness is just really a finitary, or NP-hardness rather, is really just a finitary version of undecidability in certain respects. We're asking, can basically, can a certain Turing machine run for a certain, well, anyway, it's just a finite we're looking at sort of a finite version of decidability. And so this has a natural bunch of applications. I guess this is a popular puzzle for a while, where you just try to make the sharks fit or the sea life. And I had another one here, but I guess it's behind there with soccer balls and so forth. And so the reason that these puzzles are so difficult, and honestly, I don't find them very entertaining at all myself, to be perfectly frank. But the reason they're so difficult is because you're sort of wandering around in this kind of combinatorial swamp.
Chaim,
and yes,
could you
please.
return to camera? We see it.
Yes, I'm trying to figure out how to do that. Sorry, it just occurred to me to try. Thank you.
Okay,
So,
you're back. Yes.
Thank you very much. And I should again emphasize that because of this, there's this throughout this whole theme, there's this question of what is mathematical. I think that's very important. So like, I think, for example, solving one of these puzzles is not mathematical in the sense that it's very frustrating and it's just brute force and it doesn't really lead to any kind of theory. In fact, in some sense, no theory is even possible. But it is mathematic. I think the meta-mathematical topic that I'm sort of taking here, I think is, that seems like math. But one should be warned to kind of avoid looking at individual problems. But anyway, in the years since, we had many kinds of aperiodic sets with Berger's hierarchical method. It's not the only method by any means, but it really was the dominant one for all this time. And so here's Robert Aumann again, a very elegant example. And I should say that there's an astonishing variety of tiling substitution rules. And there's really I should advertise that there's really no general theory of how to cook these things up or describe them or classify them or anything of this sort. In each case, we have some shapes and they're being made larger and then replicated. Now, these aren't aperiodic tiles, but these are non-periodic tilings with this hierarchical structure. And this one on the left here is the so-called Sphinx. And so just to advertise, I mean, Sergey was around for this. This was sort of the basis, first sort of the foundation of my career, I suppose, was that no matter what one of these you have, up to a bunch of asterisks, which are not that important, you can always cook up some set of rules that will force that structure to emerge. And so, for example, for the Sphinx tiling, just turning the crank, you come up with this crazy collection of tiles. But this crazy collection of tiles can only fit together in such a way to form hierarchical tilings with the Sphinx. Now, I want to call your attention to the fact of how ugly this is, in the sense of all these different signals and all these different little switching mechanisms at the vertices. I mean, it was algorithmically generated. There was no thought really involved. It was just turning a crank, but it was also quite complicated and kind of ugly looking. And I want to contrast that in just a moment. So we have, of course, hundreds, and then we had thousands, and then hundreds of tiles. We had aperiodic pairs, and of course we asked in a single tile suffice. That's obviously the question to ask. And I should say something about this word Einstein. So you were there when I learned about the word, I think. I don't know if you were around when Ludwig Donzer came, so did Sergey. But
yes, I was.
Yeah, so it was around 1995 that he started using this term, and he was a German speaker, so he has perfect license to come up with this stupid pun. And honestly, it's incredibly irritating in some level because it's so cheap. His whole point of calling it the Einstein was to basically make it splashy. And this year we saw all these stupid things with like the hat, Einstein wearing a hat tile and stuff like that. And I have to say, it worked. Ludwig was right. It did actually work, but I will be the first to say it is stupid and cheesy but it was very effective. So I don't know. I think we should, yeah, just keep that in mind if you ever want publicity for something you're doing down the line. Anyway, so I just want to say some of the things that were some of the misses. So one of the misses we had was around that time was the so-called Schmidt-Conway-Donzer biprism. And this is a single tile, and it admits no tiling by it will have a compact fundamental domain, a compact region that can be replicated to tile space periodically. But it does admit an infinite cyclic screw action. It admits some tilings that have these infinite screw actions. And so these days we call such a thing weakly aperiodic. That is to say, a tile or set of tiles that does not admit tiling with a compact fundamental domain, but does admit tilings with infinite cyclic actions. And this is important because these are essentially trivial in some settings. So for example, in the hyperbolic plane, almost generically, sets of tiles are weakly aperiodic. In fact, in some real sense, among triangles that admit tilings of the hyperbolic plane, get this, measure one of all triangles that admit tilings of the hyperbolic plane by themselves are weakly aperiodic. So weak aperiodicity is very weak. Again, almost every triangle that tiles, every triangular monotile in a hyperbolic plane is weakly aperiodic, almost every one. So it's very, very weak. And this was clearly not what we wanted. We wanted something stronger. In the plane, the two notions coincide as it happens, so it's not so big a deal. Another thing is that we had to be very careful about what rules we specify. What do we mean by, like, could we hide a lot of complexity in the rules? And it turns out, yes, if you have even a 2x1 rectangle, if you have complicated enough matching rules, you can do anything you like. So basically, by this stupid, again, a very cheap trick, you just take your favorite set of tiles, say Wang tiles, which are nice and on a square grid, and then you just make pixels out of them, and then you just split the pixels one way or the other. And in the same way we could recognize visually if the tiles, these marked tiles on the left matched, we could tell on the right if they matched as well. We can also get by if we allow the tiles to overlap, incredibly. We have this example, which is Penrose's kites, but modified. And then in 2009, we had this wonderful example, which has a whole rich history. And but it doesn't, it's got a kind of a flaw in the sense that the tile, this is a tile, but to make the markings work, the arrows have to kind of skip a neighbor. So this pink arrow has to match this pink arrow, but they're not neighbor to neighbor. And so we can view this in lots of ways, but however we view this, it's not very satisfying. And so the gold standard here is an unparked polygon. And then we had this very nice example just 2 years ago, which also is an aperiodic monotile, but we have, again, not nearly as complicated of matching rules as with the thing I showed you a moment ago. Very, very simple matching rules, but they cannot be encoded by the shape of the tile itself. So that's where we were. And so you know the answer to this question. Here he is. This is Dave Smith himself. And so this is a neat area because, this really relies on people like Dave. So I think like I described certain things as not being mathematical, what Dave was doing, just searching through a space, is not really the kind of thing that we like, sort of abstract reductive arguments, not grinding through looking for something. Dave had a very specific targeted place he was looking, but nonetheless, it required a lot of hands-on searching. And so, of course, he found this thing. He contacted Craig Kaplan, who's a computer scientist and math artist in Waterloo, and Craig had some software where he could generate large patches of tiles very quickly. And so this is a computer-generated picture that they generated within a few days of Dave contacting Craig. And then incredibly, they saw some structure in here, which was great. So that impressed me. And then they contacted me, and then we contacted Joseph. So in this thing, and essentially by magic, I don't think there's any way to really say what's going on here. Before I showed you tiles like the L tiles, that we had to make some modifications to the tiles. We had to put some markings or something special on them to form these hierarchical structures. And I remember I showed you the Sphinx tile, which had this very elaborate set of markings. Here, for utterly inexplicably, no markings are required, and nobody, I mean, I don't think we'll have a satisfying, I mean, I think any reason is just some sort of just so reason for now. I don't think any theory is going to emerge for this, but it certainly seems miraculous. And so the way that this works is that, oh, I guess I skipped this. Seems like I skipped a slide here. So there's this, we can, the marking, what happens is that the hat tiles, the way this proof worked was that the hat tiles, by an exhaustive brute force calculation on looking at the way the neighborhoods work, that any hat tile tiling can be uniquely decomposed into these tiling by these sort of meta shapes. And then those meta shapes have a hierarchical structure upon them. Here it's showing how the little triangular shape is made into larger and larger triangles. And then with some sort of basically a fairly straightforward argument, then it was just shown that these shapes can only form larger and larger copies of themselves in the same manner as the substitution tiling. But just as an aside of how little is known, there's actually many different equivalent substitution structures that give the exact same tiling. And so this is another big gap in the understanding that hopefully maybe the hat tiling will stimulate some interest in this, is why should this substitution structure have anything to do with the previous one? Seriously. And for that matter, why should this substitution structure, which is not, it's triangular shape, but it's not, the triangles don't line up at all with the triangles on the previous one. Why should this one, again, give the same kind of thing? Again, that's an open question. And then again, there's no general theory of that. So very quickly, Dave produced a second candidate Einstein, and incredibly quickly, Joseph realized that this is in a continuum of combinatorially equivalent tiles and tilings. And this is, again, a totally new phenomenon. Any one of these is an aperiodic monotile, and any one of these clearly is producing what is essentially the exact same tilings. To date, nobody's really defined combinatorial equivalence for tilings, but it's clear that there's some notion. I mean, we kind of have, but there hasn't really been a need until now. But these are all combinatorially equivalent, except for three special examples so what we're doing is there's two edge lengths here, and some of the edge lengths are doubled, but there's two edge lengths here. There's a long and a short. Sorry, beg your pardon. And when one of the edge lengths disappears, we have the so-called chevron, which has more combinatorial possibilities and therefore does tile periodically. And we also have the comet, which also has more combinatorial possibilities and therefore also tiles periodically. And then right in the middle, we have where the two edges are the same length. There they are. And that also has more combinatorial possibilities and also happens to tile periodically. But with those three exceptions, everything else is the same. And so on the basis of this, Joseph produced a second proof, which is brand new. So I mentioned Berger's proof. Probably 80% of the literature uses Berger's proof to show that, something in the style of Berger's proof of showing hierarchical structures. And there's really only a couple of others known. I mean, here we are about 60 years after the subject began, and there really is less than a handful. Well, actually, I should say in March, I counted about 3 distinct methods, like truly distinct ways of looking at this. Although there's probably scores of examples, but they really only fell in these categories. And since March, there's actually 3 new ones. The hat has stimulated 3 completely new methods of proving aperiodicity, which is fantastic. And this is the first of the 3 was on the original paper. And the proof is something like this. Suppose that there were a periodic tiling. Well, obviously I need artistic license to make any kind of picture of it. But suppose it's that one. Well, then there would be, the chevron and the comet, these other 2 tiles do admit periodic tilings. That's not the point. But the point is that they'd have to admit periodic tilings that were essentially the same, combinatorially equivalent to the periodic tiling by the hat. So in other words, there'd be a periodic tiling by both of the 2 on the bottom that had the exact same, or had sort of structure that was derived from the hat. But, well, but with some careful argument, and let me try to sketch that, they have to actually have the same period, at least up to affinity, up to scaling and rotation. And basically the point is this: if we look closely, any given hat is divided into polychites, these kite shapes, and it has two pairs occur twice and the others occur only once. So in order to have that work out, you have to have equal numbers of hats in every possible orientation. Simply because you have there's the same number of kites in every orientation, so you have to have the same number of hats in every orientation, which means you have to have the same number of chevrons in every orientation as well. And I guess I don't really want to try to do the argument, but I want to just say, so we have equal numbers in each orientation, and the basic idea, well, I guess I'd even skip the slide, but the basic idea is that because there are equal numbers in each orientation, you can't have any kind of periodicity, any kind of map from the lattice of the chevron tile, the lattice of periods of the chevron tiling to the lattice of periods of the hat tiling, corresponding hat tiling, has to be a similarity. It cannot be an affine, like a generic affine map. It has to be so up to rotation and scaling, it's up to rotation and scaling, the corresponding periodic tilings have the exact same period. So that's the argument there. So now why is that a problem? Well, because underneath them, they both have these triangular lattices, one by 4 triangles and one by 8, and they have the same area. So therefore there's a root 2 scaling from one to the other. But if you just look inside of a triangular lattice, all the distances between points in a triangular lattice have this nice form, the square root of a squared plus ab plus b squared, where a and b are integers. And that's pretty nice. That's a nice observation of Joseph's, I thought. And so that in particular means that if you look at this, that sum has to be a even power. Any power of the largest power of 2 that goes into the thing under the radical has to be an even power, which means that the thing, when you pull it out of that we have an integer power of 2's when I evaluate this. And in particular, the distance is a multiple of 2s. And anyway, all right. So this was more than a new tile. It's actually a whole new method. Now, I guess I'm really I want to just touch on a few other things that are related just because I have a few minutes. I want to just talk about local assembly algorithms. So this is kind of an important thing for anybody that's interested in doing this with a crowd of people, which I am, but it's also interesting in material science. For 45 years now, 40 years, there have been these so-called quasi-crystals that bear a lot of resemblance in their X-ray diffraction patterns to, say, the Penrose tilings. And it's been a question, could atoms actually form into these structures and presumably the model would be that an atom is sort of floating around and then there's some sort of local configuration that tells that it could plop right in. And that cannot possibly be what's happening. And it turns out that's, for one reason or another, that's not what is happening with quasi-crystals, real physical ones. And it's not happening here. Oh, here's some more kids having fun. Because a great result is that there's no perfect local assembly rule to assemble the hat, or for that matter, really any other aperiodic set of tiles. And this goes back to Dworkin and Shea in 1995. This was in the context of people wondering about, can you make physical materials with these properties through, again, some model that is how we might envision, something kind of swimming around and then it sees some favorable local configuration and plops down in. Well, the answer is no. So for some deep reasons, which I'm not going to go into, every set of tiles that admits a tiling, and again, this is a deeper result, also admits a tiling in which for any radius, any patch of that radius appears infinitely often. So that's kind of a lot of quantifiers there, but the point is that I can always find some situation like this. For the hat tiling, we just explicitly do it. So suppose that we have you fix some radius, which is going to be your field of vision. And in that field of vision, you're going to just be able to determine, supposedly, can I place a tile or not? And suppose this is how big our field of vision is. I locate three regions that are in two independent directions from each other. And there's some band of tiles that connects from one to the other. And I just use that band of tiles to create a grid like this. You see, if I can connect from here to this to here, I can also continue the same way to the lower right and to the upper left. And so in this manner, we can form this grid. But the whole point was this is a non-periodic tiling. So I already screwed up. There's no way I can complete this to a tiling of the whole plane. And yet it was perfectly fine within any of this alleged window that I was looking around in. So that's a very nice argument. But I'd just like to sort of say that there are plenty of other ways around this. If we allow additional markings, or we have a special seed tile again, or we can do various kinds of random processes that succeed within epsilon of perfection. There's all kinds of ways around it, but this self-assembly of aperiodic tiles is pretty neat. So this is something called the Robinson tiles that are self-assembling. This is not the hat tiling, but this shows kind of one way to have things. What you can see is that various kinds of signals are being sent out. They reach each other, and then when they meet, there's the possibility of some other signal, being generated that then gives enough structure to complete the tiling. Okay, well, I'm out of time, but just in case I had other settings to discuss. So I just will say that this kind of game works in very, very generally. So we can play this in the hyperbolic game. We can play this with multiple kinds of tiles. We can play this where we allow only translations. We can play this in higher dimensions. Now there's a whole industry of doing this kind of implication on Cayley graphs of groups, although we have to change all the definitions. And I just want to say a couple of quick words about this. So there's been a lot of recent work by Greenfield and Tao. I think I misspelled her name. Rachel Greenfield and Terry Tao, for moving things around by translations only, but they use a lot of extra dimensions. So really reasonably, I'll just skip that. In the hyperbolic plane, we have basically this situation. This is the situation in the hyperbolic plane. I'm not going to go on to about that. And then this is something about, I'm going to skip that slide, but that's in. I guess I do want to say something about in the general group situation, this is an important result. I really could have made this a bit better at the bottom there. On arbitrary groups, on an arbitrary Cayley graph, we can ask if a so-called subshift of finite type is empty or not. So a subshift of finite type is an assignment of markings to the group elements that satisfy some sort of local configuration rules, some sort of local atlas. And I think so there's all kinds of stuff. Just this year it was shown that it was finally shown some very nice examples that the lamplighter groups and the all word hyperbolic groups have undecidable emptiness problem. That's to say the domino problem is undecidable in effect in arbitrary word hyperbolic groups. That's pretty cool. But the result at the bottom, which should have gotten a theorem, is that in fact the existence of, say, a strongly aperiodic subshift of finite type, or whether or not the emptiness problem is undecidable, is actually a QI invariant. So first of all, that implies that for any given group, it doesn't matter which Cayley graph you use, but also, once you answer the question, for example, for one-ended hyperbolic groups, you've answered them for all one-ended hyperbolic groups. And this is a result from David Cohen, 2017. And I guess I really should make that a theorem, David Cohen slide. But just to wrap it up, I think there was a lot of concern about whether or not there was the hat tiling is one tile or two. whether reflections are allowed. I think that this is a puzzle, indicates that there really are the same shape because it's a puzzle. Otherwise, it wouldn't be a puzzle, right? But mathematicians seem perfectly content to call the hat tile one tile, most of us. Euclid himself in book 1, prop 4, takes the position that two triangles are equivalent, he says. Well, what does that mean? If they have the two sides and the interior, the angle between them equivalent, well, that clearly includes reflections. So whatever he meant by equivalence included the possibility of reflections. In fact, book 1, prop 4 is a proof by supposition. It's one of the few in Euclid's Elements where he actually seems to be explicitly sticking one triangle on top of the other. So I think it's pretty clear, if we want some authority, that there really is only one hat. But but physicists naturally disagree, and that's fine. So luckily, there was an aperiodic chiral tile, the spectre, the so-called spectre. Just by, again, there was no reason to really expect this. It's just sheer miracle. But this tile, this is the one where all the edge lengths were equal. It had extra combinatorial flexibility, which allowed it to be periodic if we allowed flips. So just remove flips. And, you know, Dave is an amateur mathematician, so-called amateur mathematician, but this was his insight. And so I think that Dave, that's a very mathematical insight. So whatever we want to call Dave, I think he's certainly a mathematician, for noting that this was even possible, even worth looking at. And he was right. And so by modifying the edges, we can ensure that we can't flip them over. The last thing I'd like to just quickly conclude is, of course, if you've heard of this at all, you're probably aware that it really entered the popular culture in some ways. And so there's this fantastic variety of people rendering hats and specters. It's just, I think any of us, honestly, I'm probably the only mathematician around who can show anything like this. I mean, it's amazing to be able to see people reacting to this work in kind of real world. So here's these incredible variety of things. These were all made immediately after it came out. But then the soccer ball by John Paul Wheatley, these kinds of beautiful tilings, a shot glass, which is periodic one way around, but you can't expand the period the other way. Cookies, quilts, this is some sort of ray trace thing. This is fabric, and beer and tattoos. So just there's about 3 days left. If you want to win some money, there's actually some corporate sponsors have given very generously to this kind of contest to stimulate this. And that's closing in just a couple of days, but that's going to be pretty great. And I think that, and you know, you just emphasize 20,000. So I think that's it. Thank you very much.
Thank you, Chaim, for your marvelous talk. Any questions? Either ask by chat or unmute yourself and ask directly.
And now I can look in the chat. Somebody. Hello.
Yeah, I have a question. So this the hat tile has 12 edges. I guess it's a polygon with 12 edges. Is that the minimum possible number of edges for, or is there anything known about that?
No, nobody knows anything. I think actually I could just preemptively say for a lot of the questions, nobody knows anything. How's that?
Well, you know, it's bigger than 4, presumably.
Yeah, I mean, all pentagons. So we know that all convex pentagons, we know exactly which convex pentagons tile the plane, but we don't know, for example, which non-convex pentagons tile the plane. Or how, you know, I mean, that's just pentagons. So
there could potentially be an aperiodic pentagon tile, or
I mean, I think probably somebody could rule that out. I just am saying that nobody has. I should also say something about that too. Like when I didn't mention this in the talk, but you saw those crazy examples from Robert Myers. I think it's also clear that like a year ago, I was asked, is there an aperiodic monotile? And I think prior to the hat, everybody expected to be something like this, but much, much worse. That you just somehow encode some sort of computation like in the jiggy jags, you know, like But let me try to answer some of the questions. So let me try the easier one first. How did you get there to the substitution? You mean for the, do you mean for the substitution for the, in general, or for the hat tiling?
It seems to make sense. It looks like Dave Smith was like, let's take these half kites. That seems like a fruitful place to start. Let's see what kinds of shapes we can make from half kites, and then let's look at Heesh numbers. That seems to me, that makes sense. That's a place that someone would start, and then I get a really big Heesh number, and we'll see what happens. But
That's right.
how did you go from there to you have these two sort of substitutive conceptions? How did
Okay,
you?
so I think the right answer is that we did the obvious. We followed the historical precedent and tried to see if the same game plan that had worked for decades might work. And by some miracle it did, but there's no reason it had to, so basically Craig stared at it and found that first initial substitution structure, which was there. Like, all I can answer your question is like it was actually there to find, right? And then since then we've seen other kinds of substitution structures that have other ways of looking at the same thing. It's kind of like the parable of the elephant and the blind men. We don't quite know what we're looking at, but it didn't have to be there. And in that case, we would have just been kind of stuck. So, but it was the natural thing to try, just because that's what we knew. But on the other hand, that it was there is kind of interesting too, because see, like in those decision algorithms I was describing, well, the first thing to try is, do you tile at all? And no, if you don't, you'll crash. The second thing to try is, well, do you tile periodically? And if you do tile periodically, you can discover that. Well, another thing, that's sort of the next simplest thing might be, that nobody's formulated this. It's a vague idea, but this hierarchical structure is also very rigid, and something that in some sense seems like something that if one could just define it right, that you'd be able to algorithmically determine whether or not a given set of tiles admits a tiling. In some sense, it seems to me like maybe that the substitutive hierarchical structure is, okay, it's not quite as simple as periodic, but it's very, very simple. And so in some sense, maybe it's natural that it would arise quickly and readily. But honestly, I'm just spinning air. Of course, we don't really know. I'm just giving you a just so story. But I think it's a good one, I think. And maybe 50 years from now, it will be backed up. But maybe to touch on Daniel's, I guess I did talk about a bunch of undecidability problems. Is there one specifically that you meant? Or what did you mean? Maybe you can speak, turn off your mic, or could be unmuted. Are you here, Daniel? Are you muted? I can see your camera's working. You're unmuted.
People can unmute themselves now if they have a question.
Okay. Daniel? It's okay. Well, anyway, the whole thing, I'm not sure really which, there's this whole web of decidability questions that are all sort of underlying this. They all come from the halting problem. They're just interpreting the halting problem in different kinds of ways. But
I have a comment, which is more of a kind of side remark. So in spectral geometry, there is a famous Poyer's conjecture about eigenvalues. So it's a conjecture, the inequality for Dirichlet and Neumann eigenvalues, that Poyer conjectured for all domains, but he actually proved it only for tiling domains.
Yeah.
So basically, each time we have a new tiling domain, so automatically we have a whole series of eigenvalue inequalities that we know for this domain.
Yeah, that's right. I'd heard of. I don't know much about that, but I'd heard of that.
And what is known about high dimensional monotiles?
Oh yeah, so in Euclidean space, I think this. So now that we know where to look, it's pretty obvious that in Euclidean space there's going to be lots and lots of these, and in 2 dimensions. So the way that there aren't very many analogs to something like the polykite in 2 dimensions. The two, there's not a lot of room to kind of work around. And again, that's another. Sorry, I'm living in New York. There's not a lot of Okay. Well, I was up. I took advantage of. Okay, so in 2 dimensions, there's not a lot of analogs. There's like, very, very little to work with in terms of chopping up a regular tiling and maybe looking at pieces and something to explore. But in 3 dimensions, there's several interesting tilings of space that would work great as places to look. And it's just a matter of time. In 20 years, if there's interest, and I think there's enough labor to get this done. There surely will be lots and lots of them in 3D. Because, for example, this chunk here is based on a tiling of space by the truncated tetrahedron. You can't, whatever. And it has sort of this natural division into smaller pieces. Well, then just explore these. Surely some weird arrangement of these, it's definitely worth looking at, And then similarly, the truncated octahedron has filled tile space, and there's lots of ways to chop that up into nice, neat pieces. So the answer right now is that none are known, but plenty are expected for aperiodic monotiles in higher dimensions. Whereas in 2D, I don't know. I'm not really sure. It'd be so strange if this was the only example, but that's possible. And then I should also emphasize again, of course, that the monotile problem might be undecidable, which would mean that particularly we'd have lots and lots of these.
Thank you. More questions?
Infinitely.
Oh. Can you see chat?
Yeah, so May says we have unreflected tiles tend to form long chains. So actually, honestly, that doesn't even seem like that. Maybe in March we observed it, but now it's like trivially true. So let me show you why. I guess that's a difference of a few months, something that seemed mysterious, and now it's like, oh yeah, of course that's true. Here's the proof. So let me try to share my screen. I just want to show you. I have to say, I really like the beer and tattoos. That's like pretty phenomenal.
Tattoo already? Have you made it?
What's that?
Have you made a tattoo for yourself?
No, I'm not going to get a tattoo. But it's funny that somebody thought that they should. Okay, so this is another substitution tiling. I don't have the rules, a slide with the rules, but you can see something about the way it works, and the way that it's colored has these chains. And actually in the rule itself, explicitly, you explicitly have the chains being replaced with longer chains, with longer chains, with longer chains. So it's just, the rule makes it utterly, the substitution rule that is giving rise to this structure, it makes it transparently obvious. Whereas we didn't know this. This particular rule came from these 2 Japanese tilers, Akiyama and Kiri. Oh, sorry, Arakai. So yes, we do. It is now it's not only provable, but very transparent.
More questions? If there are none, well, thank you again.
Thank you.